So we want to continue with our lecture on the Jacobi method. In our last, we looked at the method and we said you can use equation 19 as an iterative scheme to solve linear system of equations. Okay, so we want to look at this example here where it's a matrix 3 by 3 matrix multiplied by your x is equal to the right hand side of it. So B, if you apply 18, all right, which is split it into the diagonal matrix, the sum of the lower and then upper triangular matrices plus your B10. So that is this equation here, right? Equation 18. That gives you this, and then you can write this as a system of equations, right? So if you just write that out, you're going to get 3 equations, which is given by this. So often for all the iterative methods, this is important. For all the iterative methods, you are actually solving equations like this. You solve this first one, all right, for x1. You solve for x2 here, and then you solve for x3. So initially, you give it an initial condition, initial values for the x at r, right? All these are given, and then you solve for r plus 1, and then you go on. What you found, you plug them back into this and solve for the next values of x and continue in that order. So you can start, for this simple example, you can start with a 0 vector for x0 and plug it into your scheme, your code. I'll give you a MATLAB code that I used to do this. It is actually at the end of the presentation. Okay, so you go through this, and after about 28 iterations, you end up with this solution. Okay, you get this solution for if you specify a tolerance of about 10 to the minus 4, right? In other words, when you continue this process, and then finally when r plus 1 minus x, when the difference between the two, okay, is less than this, you stop, and then your solution is given by that. Okay, so that is how you iteratively can solve the system of equations to get this. And then so that was the Jacobi method. All right, so pay attention to the simple equations. They are simple, but they have a lot of information. So we are going to move on to the Gauss-Seidel method. Before we do that, I'll just explain something I'll explain later on. Okay, so how you improve upon this is this, or how the Gauss-Seidel method improves upon the Jacobi method is that what you do is you apply, after you solve this first equation for x1 at r plus 1, when you come to solving the second equation, all right, you don't use x1 at r, because you already know the value at r plus 1, you plug x1 at r plus 1 here instead of x1r, because you already know that, and solve for x2. Then when you move to x3, instead of using this again, you use what you have already solved, because that is known and it's an improved value, so you put it here, and you do the same thing for here. You have already solved for an improved value, which is x2, so you take x2 and plug it, x2 at r plus 1, and plug it in here before you solve for x3. So you see that it is an improved method to the Jacobi method. So that is what our next few slides will be explaining. Okay, and so the Gauss is an improvement, of course, on the Jacobi method. It's obtained by using the newly calculated elements as soon as you get it, and then as soon as it's available, you plug it into your next equation and solve for the new values. That is what this is explaining, which means that the elements that are multiplying the lower triangular matrix in equation 18 are known, and you could place them on the left hand side of the iteration. Note that these guys that you are replacing with this, these guys are actually elements of the lower triangular matrix. This guy, that, and this, these are elements of the lower triangular matrix. So you could actually move these guys to this side, to that side, okay? And so that is what this general form is doing. So from 17, which is this equation here, you leave the lower triangular matrix and the diagonal matrix on the left hand side, and then you take the ux to this side, and you have negative ux at r plus b, and that gives you an iterative scheme. So this scheme now is the same scheme that we just explained, which is an improvement of the Jacobi method, and it's called the Gauss-Seidel iteration. Okay, so we'll look at various forms of this that you can actually use to solve the system. Okay, so again, you can rewrite this, right? From here, you can if the inverse of this exists, okay, you can multiply both sides by the inverse of that, and that gives you equation 25. Now, so to get a better understanding of what equation 25 is doing, we know that we can actually rewrite 24 in this form, right? Leave the diagonal and take the L and U to the side, okay? And then when you do that, you can also pull out, know that this is still the same as that, right? And then note I'm just adding and subtracting dx to the r. So this is the same as this, but they cancel out. So this is still the same as that, okay? And now if I multiply through by the inverse of d, okay, this d goes, and I'm left with x to the r, and I have d inverse multiplying by all of this, and that gives me this thing here. And so you will see that the new value, the new approximation here, is equal to the old one, right, plus some kind of a term which is referred to as a displacement. Okay, so you have the old one plus some kind of a displacement, and that is how the scheme develops or evolves. Okay, note that even though this is x to the r plus 1, for your initial equation you don't have a lower triangular element. So for the initial equation, this actually goes to 0. You don't have that. So all you have is this, and then in the subsequent ones this appears, right? Okay, so this gives more information about how the system evolves than the previous one. So that is how the Gauss-Seidel thing evolves. So we'll look at an example of it, the Gauss-Seidel method. Okay, so here is the same example that we solved using the Jacobi iteration. So now we want to use the improved method of the Jacobi, which is Gauss-Seidel, and see what we get. Basically, you want to see whether you are doing a better job in terms of the number of iterations that you need to go through before you end up with your final solution. Okay, that tells us whether this is improved. And so you have the same equations, but as we said before, so now if you go back to equations 21 to 23, what you find is that now instead of x1 at r, right, we are replacing it with x1 at r plus 1, because we have just computed it in the first equation here. And then this remains the same. When we move to the last equation, x1 is replaced with x1 plus r, x2 is also replaced with x2 at r plus 1. I mean r plus 1, r plus 1, because we know them. And then you solve it in that order. Okay, so again, if you code this up and solve it, what you find is that after 22 iterations, you end up with the same solution, the same, if you use the same tolerance. Okay, so in the previous one we had to do, let's see, we had to do 28 iterations before we end up with this solution. With the improved one, you do just 22 iterations with the tolerance of this before you get your final solution. Okay, so that's an improvement. So in the next video, we want to look at how do you increase the convergence rate, right? So that's even faster than the Gauss-Seidel, right? So there are schemes for doing that. So I'll talk about that in my next video. Okay.